Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to a review for my pre-calculus students, and yours as well, I suppose, on the difference quotient. You should have been pre-exposed to this in college algebra. However, if you were not, well, I'll cover it a little bit here. The difference quotient is one of the most important features of pre-calculus that gets carried over into calculus. It is really important for calculus, in fact. The difference quotient of the function f is defined to be f of a plus h minus f of a all over h. You should be able to evaluate f of a plus h. I'm just letting you know, one of the most common mistakes I'll see is people will say, oh, that's the same thing as f of a plus h, or f of a plus f of h. You should be well beyond that. You should know that those are not the same as f of a plus h. Totally not the same. It is an order of operations issue. So anyhow, there is, by the way, a secondary or alternative form that's used in calculus, and that is f of x minus f of a all over x minus a. But to be honest with you, the first form, this guy right here, is the most popular form in calculus. The second form does creep up in calculus every once in a while. It's not hard to deal with either. As I state down below, really what the difference quotient is a slope of a line connecting 2 points on a curve. For example, somebody comes in and they hand you a function that looks like this. Let's just pretend. And you want to connect the point a, comma f of a, to some other point on that curve. And that other point I'll park right here for now. And it's a slight wiggle away from a, so its x value is a plus a little bit, and the function value is f of a plus that little bit. Well, if I connect those two dots with a line, then we can compute the slope of that line. Remember, slope from your elementary algebra days back in middle school or something like that is just difference in y over difference in x. Specifically, it's y2 minus y1 over x2 minus x1. So let's pretend as though the red point is my x2 comma y2 and the blue point is my x1 comma y1. If that's the case, the second y value is f of a plus h, and the second x value is a plus h, minus. The first y value, y sub 1, is f at a, and its associated x value is a. If I were to clean this up, this would equal f of a plus h minus f of a all over h. And that is the difference quotient. It is just the slope of a line connecting 2 points on a curve. It's called the slope of the secant line, actually. So let's see how to use this in action. Find the difference quotient for the given function, which is z of p is equal to square root of 2p minus 1. Simplify your answer, if it's possible. Then we're going to go to Desmos to demonstrate the meaning of the difference quotient, which is basically what I just did on the previous page, but it's good to see it on Desmos. And then we'll investigate more details about it. But let's by hand find the difference quotient for this function. Now recall, the difference quotient is the following. However, in our case, our function name is not f, so we have to trade that out. Also, they tell us that later on we're going to be evaluating the difference quotient at the point 5 comma z of 5. I'd like to actually showcase that here as well, but let's just keep this very simple. Let's keep it just like this, the standard difference quotient. What you're going to do is evaluate this very first function, z of a plus h. So I'm just going to take this function z, and instead of plugging in p, I'm plugging in a plus h. And that is z evaluated at a plus h. Now I'm going to subtract from that z evaluated at a. Now that I've done that, we go ahead and divide this whole thing by h. Now if you stare at that and say, oh, I guess we're done, you're wrong. You actually have to rationalize that numerator. That's a very, very important concept in calculus. And so you do have to do it here. Multiply both numerator and denominator by the conjugate of the numerator. That is, multiply both numerator and denominator by that expression right there. We're really multiplying by the number 1, but it's a very special form of the number 1. As I have mentioned in a previous video, maybe not in this course that you're taking, but I have mentioned it in previous videos, so you may not have seen it, but you do not multiply out the non-conjugate pieces. That is, that denominator is not a couple conjugates multiplying each other, it's just h times that conjugate. And so you don't want to distribute that out. You do not bother distributing out non-conjugates in calculus. But the numerator, all this stuff right here, you definitely want to distribute all that stuff out. Luckily, this picture right here that I'm calling F, minus that picture right there, which I'm calling L, is the same thing as this picture right here, which I'm calling F, plus that picture that I'm calling L. This is actually a difference of squares. And when you multiply out a difference of squares, it ends up being the square of the first minus the square of the last. So that's a really cool trick when working with conjugates and multiplying by conjugates. You're just going to take this first object and square it, which leaves you with 2 times the quantity a plus h minus 1. And then you're going to subtract off the square of the second term. Very important note here, you should use parentheses whenever you're subtracting something, especially if that something has more than one term. Now all you're going to do is simplify this statement. I'm going to distribute that 2 through, and obviously the negative as well, and combine like terms in the numerator. 2a minus 2a, those kill each other off. A negative 1 plus 1, those kill each other off. And you're left with a 2h over h times a bunch of ugliness. Now, if you've done your work correctly, every time you do a difference quotient, you should actually cancel out the h's. Not all the h's, but a single factor of h out of numerator and denominator. That's what should happen every time that you work on a difference quotient. And we arrive at this statement right here, which we technically can do nothing with. However, I do want to mention before we go into Desmos is that we are eventually going to say, well, I'm interested in finding out what the value of this difference quotient is if a is equal to 5. That's really what's being asked here. We have 2 points, 5 comma z of 5, and 5 plus a wiggle, comma z at 5 plus a wiggle. And that corresponds to this idea right here that we showed a moment ago. Our red point is going to be 5 plus a wiggle, comma f at 5 plus a wiggle. And our blue point, which I call the anchor point, is going to be 5 comma f at 5, although our function actually has a name of z. Fine, z of 5. So in reality, for this problem, when we go over to Desmos, we are going to lock these values of a in to be 5. But technically right now, this is just the difference quotient that you're looking at. It's just to let you know that sometimes they give you concrete values for what a is. So they might say, find the difference quotient for z of p, and then let a equal 5. Or sometimes they may even say something like, evaluate z of 5 plus h minus z of 5 all over h. They might do that too. It really is the same mathematics though. Instead of a's, you would have 5s, but it's all mathematically equivalent. Let's go ahead and hop over to Desmos to take a look at this. All right, here we are in Desmos to visualize that difference quotient. And I already have set in there z of p is equal to the square root of 2p minus 1. Remember, we're interested in our anchor point being 5 comma z of 5. You can actually do this in Desmos very easily. Just type in parenthesis 5 comma z of 5. Obviously, you can calculate z of 5 very easily. That would be square root of 9, which is 3. However, you can see that also Desmos can compute it pretty easily itself. Let's turn off the grid and put it in projector mode. That way it's a little bit easier to see what I'm doing here. Now I'd like to create a second point. And the second point is going to be a slight wiggle away from this point 5, z of 5. So let's go ahead and create that point. The x value will be 5 plus h, and the y value will be z of 5 plus h. And it asked me to add a slider. I'm totally going to do that. We're going to allow our h values just to go from, let's say -2 to +2. Let's just keep it easy here. And the step size, I think it automatically determines 1, but I'm going to do 1/100th. Now, right now the step size is 1, and you can see that green point right there is 1 unit away from our anchor point. And then I can increase our little step size there or decrease the step size and so on and so forth. I could do it in both directions. Remember when we talked about the difference quotient, it was said that this is the slope of the secant line or the slope of the line connecting 2 points. That's really what the difference quotient is a slope of a line. So let's go ahead and create that line. We have 2 points, this green point, this blue point. Let's go ahead and do that. The equation of any line is just y minus y sub 1 is equal to the slope times x minus x sub 1, where x sub 1 and y sub 1 are points on your line. Well, 1 point will always be on our line when we're dragging this second point around. The 1 point that will always be on our line is 5, 3 or 5, z of 5. So I'm going to let x sub 1 be 5 and y sub 1 be z of 5. But yet it still doesn't know what m is. And that's because m is the slope connecting this anchor point 5, 3 to this point that I'm dragging. Well, remember, the slope is actually the difference quotient. So if I replace m here with a fraction and I type in the difference quotient, which remember was f of a plus h, except our function name is z. So z of, I'll type in a plus h first. We're going to change that, but z of a plus h minus z at a, and that's all over h. Well, in this case, our anchor point is at a equals 5. So I'm just going to replace those a's with 5s. And notice what we get. This beautiful line. And now when I drag this, you see that that line just connects these 2 points, the anchor point at 5, 3 and whatever the green point is. Let me change what h is allowed to be. I just gave it a wider range so I can drag it a little bit further. But you can see actually pretty nicely there when I get around there that this is definitely a line connecting 2 points, and the difference quotient is going to be the slope of that line. That's literally what I typed in there was a difference quotient. So, and I typed that in for the slope, and so therefore that is definitely the slope of this line connecting these 2 points. The goal in calculus, just to give you a heads up, is to drag these points closer and closer together, so close that they're almost touching. Technically, they can never touch. You don't want them to touch because if they touch, then there's no wiggle here and you have a division by 0. So you don't want h to be 0, but you want to, see what happened there when I let h be 0, the line disappeared. So you want them to get really close to one another, but you don't want h to ever become 0 because once you do, you don't have 2 points and you can't create a line. Anyhow, that is a visual of the difference quotient. Now that we have a more solid foundation of what a difference quotient is and what it represents, let's go back to the mechanics of the by hand computations of the difference quotient. So here is a rational function, h of u is equal to 2u plus 1 over 3u minus 4. This is one of my favorite styles of functions to give for difference quotients. The difference quotient for this function would be h of a plus h. Well, that's an unfortunate naming convention. How about we rename this function to not be lowercase h, but instead a capital H, because, well, it's less confusion. So we have capital H evaluated at a plus little h minus capital H evaluated at a, all divided by little h. little h being the wiggle away from our anchor point A, capital H just being the name of the function. So taking a look at our function here, instead of u, we're going to plug in a plus h. So let's go ahead and do that. So that is capital H of a plus h. And then we're going to subtract off this capital H function evaluated at a. So we're going to let u equal a. And there we go. Now, this is all over h. That's very commonly forgotten, by the way, but that's the most important part, in my opinion. And you can take a look at this. This is called a compound fraction. So you should have already reviewed, or you should know about how to simplify compound fractions. All you're going to do is multiply numerator and denominator of the major fraction by the LCD of all the minor fractions. So in this case, we're going to multiply top and bottom by 3 times a plus h minus 4 times 3a minus 4. And we do the same multiplication through the denominator. Again, note that I'm only multiplying by the number 1 here. It's just a fancy form of the number 1, but it is the number 1. When I distribute this LCD through the numerator, the 3 times quantity a plus h minus 4s cancel in that first term, and you're left with a beautiful 2 times the quantity a plus h plus 1 times the quantity 3a minus 4. Take that same factor and distribute it to the 2a plus 1, the second term, and you'll see the 3a's minus 4 will cancel. So you have a minus, and remember when you have a subtraction going on, you definitely want to use parentheses after it. And we're left with 2a plus 1 times the quantity 3 times quantity a plus h, and then minus 4. All of that will be divided by, and again, in this case, do not bother distributing out that h. The rule of thumb is that if you're multiplying numerator and denominator by an LCD, you only bother distributing out the stuff that caused you to multiply by the LCD in the first place. For example, those fractions in the numerator forced us to multiply both numerator and denominator by this 3a plus h minus 4 and 3a minus 4. That denominator actually didn't force us to do any of that. It was only the fractions in the numerator. So that denominator will not be distributed through that blue ink. It'll just hang out in front of that blue ink. Trust me, if you were to multiply out that denominator, you would be doing a tragic disservice to yourself. Now what I'm going to do is start distributing things out. For example, this 2 I'm going to distribute to both that a and that h, and this 3 I'm going to distribute to that a and that h. And actually I decided I'll go ahead and distribute that 3 to the a and h downstairs as well. So that just made it a little bit cleaner, that's all. Now comes the fun part. Lots of distribution. So I'm going to distribute through this trinomial upstairs to this binomial. So distributing all this stuff here, and then the 2h distribute through, and then the 1 distributing through. Let's go ahead and do that. Notice how I color coded it with the lines or curves that are the arrows I've used up above. That's just to help you out, to show you how I arrived at those values. Now I'm going to do the same thing with this 2a to each of these 3 objects here, and this 1 to each of those 3 objects there. There you go, and it's again color coded. And then downstairs, remember, do not distribute out that denominator. And now you guys are experts at this, so I don't need to walk you through it, but you have 6a squared minus 6a squared. You have a negative 8a minus a negative 8a, so those cancel. You have a positive 6ah minus a 6ah, those cancel. Let's see, you have a 3a minus a 3a, those cancel. You have a negative 4 minus a negative 4, those cancel. So in the end, you have negative 8h minus another 3h, or in other words, a negative 11h upstairs. And as I mentioned previously, those h's, if you've done everything correctly, should be able to cancel at this point, and you're done. There is still an h in this, but it's not what I'm talking about when I say the h's should cancel. When I say the h's should cancel, I mean there should be factors in both the numerator and denominator of h that will cancel beautifully, but there still might be an h locked inside parentheses. That's perfectly fine. So this is the difference quotient for that function up above. Just letting you know, this skill is very critical for your success in calculus. So if at all possible, practice as many of these problems as you can. You won't be able to succeed in calculus without knowing the difference quotient and being able to work with it. Luckily, it's actually not too terrible. Anyhow, we're done with this video. In the next video, we'll do one last review on functions, and that's piecewise defined functions. And then we're off to the races to another set of videos.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine. Just